you want to intro?
Yeah, all the other microphones up here seem to be IPv4 ones. I'd just like to introduce our next speaker, which is Dino Farinacci from Cisco, with his colleague Clarence Fulsfuss. We'll be talking about some solutions for IPTV.
Okay, can everybody hear me? Yeah, okay. So we're going to talk about an idea called multicast-only fast rerouting. And we'll describe the problem statement, solution statement, give two examples how it works, and talk about the failure detection mode. And then hopefully we'll have about 5 minutes for questions. Clarence and I could field questions. So problem statement, packet loss is the greatest impact on video applications. The mean time between artifacts for human is about 2 hours. That's kind of the expected norm in the industry. There's been data that Clarence could give references later that usually the node and link failures have a mean time between arbitration or between artifacts at around 100 hours. So we don't think network failures really can impact very much. So we're just trying to give you a level set on we're actually solving a very, very small portion or small percentage where failures occur. Losing iframes with 50 millisecond rerouting has some visual impact, but pretty much the same as 400 milliseconds. So that's kind of interesting as well. So when people say they need 50 millisecond failover for video applications to work, you have to ask the question if that's really true. So let's look at some switchover timeframe requirement ranges. We believe with tuning and fast convergence features of routing protocols that we can get to 500 milliseconds to a second of switchover times. We've also seen cases where we can actually tune things much better to get between 100 and 500 milliseconds. And I think in reality that's what's really needed. The 50 millisecond to 100 millisecond time frame is something that's probably outside of what the unicast protocols could do, so we're going to focus this multicast only fast reroute for the 50 millisecond time frame. And there's a perception is that is what's needed, so we're going to try to do it as fast as we can, and then people that feel they need that could use this solution. So multicast streams need resiliency for network outages. That's the basic problem statement. We need fast switchover times with near zero packet loss. You ask the video application guys, could we drop a few packets, one in every 100,000? They say absolutely not because everything goes bonkers, right? I don't know if that's true, but that's what they say. So we're going to try to shoot for the 50 to 100 millisecond range and see if we can solve it with this problem, with the solution, I mean. There's some existing redundancy models that basically says you could have one source that's sending a video data stream that sends multiple streams on diverse network paths. They could do it from a separate source address, separate group addresses, doesn't matter, it just emits basically 2 streams. Or you can have multiple sources send the same stream on the same S&G on different network paths as well. And then devices that are near the receivers drop the redundant frames and only forward what they need to. And if they detect a failure, they could go accept the other data stream. So these are called source redundancy models. But to really have a good, fast switchover, you can't use messaging. You can't use protocol on network messaging because it takes too long. There's propagation time over the links. There's queue and processing time in the routers. So you need something to be fixed or repaired or in hot standby before the failure occurs. Okay, so you have to make before break. It's just that when you're working at these time frames, that's what you have to do. You can't depend on unicast routing convergence because we believe the fastest we can get it is around the 100 millisecond range. And if we want to go faster, unicast routing may take too long for this level of switchover. And of course, it always needs to be relatively low cost. I don't know if appropriating servers is the best way to do things. So if we try to solve the problem in the network, it's probably going to be lower cost. And of course, everything nowadays on the internet has to be incrementally deployable. So let's talk about this multicast only fast reroute. The reason we call it multicast only is because the multicast protocol, the single protocol that's going to solve the problem, is not going to depend on other parts of the system or other parts of the protocol system. So it's going to solely depend on PIM. And PIM doesn't have, PIM or the MRIB or whatever your implementation does not have to wait for the unicast routing protocol to converge. It's going to make decisions unilaterally. And of course, it's going to be made before break. And it's an alternative to the source redundancy model, but the redundancy or the extra data that's sent on the network is done inside the network rather than on the sources. So you don't have to provision extra sources. You don't even have to sync data streams because we won't deliver duplicates to the receivers. So that's important. And actually, the upstream routers don't have to support this. So there's only parts of the network where you may have to put this in. So it's not like your entire ISP network or enterprise network has to support this. To make it work lean and mean and simple, there are disadvantages associated with it. This usually depends on equal cost multipath. Okay? It could also work for non-equal cost multipath as well, but you could do that by making longer paths through extra hops look like equal cost paths from a unicast routing perspective, or you can use feasible successor technology as you see in EIGRP. But we've also been able to make extensions for ring topologies where not all nodes on a ring are actually equal cost to the source, and we'll actually show you an example of that in a minute. So what happens is the disadvantage is that redundant data does go on some parts of the network, and that's the cost you have to pay to make before break. But as the membership becomes more dense, that's less of a problem, and we'll show you with an example here. Okay, so we have this, we're going to focus on router D, which is at the bottom. We have a source at the top and a receiver that's directly connected to D. Just assume the source and receivers are off Ethernets off of those boxes. What we want to do is we see that D has an equal cost path to S through B and C. And we know that D typically today running PIM will send a PIM join message choosing one of those equal cost paths. Let's say in this case it chooses C. Well, that join goes to C, C propagates it to A, and then we find out that the data path comes down on the right-hand side. Pretty basic stuff, okay? The extension, what we want to do is we want D that's configured to do multicast only fast reroute to actually send an alternate join. This is safe to send an alternate join through B because we know it's the shortest path towards A, so we don't have any routing loops. We know we can send unicast packets both ways to S without looping. We can certainly do that with joins. So we send this join to B, B propagates it to A. What's interesting to see is A thinks that there's two OIFs leading to two possibly different receivers. But in this case, we're tricking it. It's actually the same receiver, and we're pulling down data on both paths. Well, that dotted line path on the left-hand side is the repair path that's ready to go. And what will happen is when S sends data packets, it's going to go down both paths. So the left-hand side of this topology is actually wasting data. But of course, D will RPF check when data is received. It'll RPF succeed when the packets are received on the right-hand side, but RPF fail when they're received on the left-hand side. So the packets are dropped, so the receiver only gets it doesn't get duplicate packets basically in this scenario. Now, yes, we're wasting bandwidth on that link, right? Packets don't have to come down there, but we want to receive it because if there's a failure on the DC link or the C router or the CA link, we want to be able to receive data right away. We're also wasting bandwidth on that link as well, okay? Now, the impact of wasted data or redundant data is minimized if there's a receiver upstream. If there's a receiver off of B, then you find out that there's only wasted bandwidth. There's only wasted bandwidth on this link, and there's not wasted bandwidth on that link because A would have to forward to B anyways to get the data to the receiver. So as the membership becomes more and more dense, the redundancy is less of an impact. Okay, so that's the basic the ECMP example. So what happens is now is when C fails or the DC link fails, D makes a local decision to accept packets from B, okay? When it does that, note that this thing's going to go away when I hit click. Okay, that link fails, D detects the failure, and then what it'll do is I'll start accepting packets there. That will become my new RPF interface. That decision is made locally by the implementation. There is no signaling going on. Nobody else has to tell what's going on. Now, the big question is, well, it's easy to find out that the DC link fails because it's directly connected to D. And it's possibly easy to find the failure when C fails, the node fails. But it might be hard for D to notice that the AC link fails. And then later in the presentation, we'll tell you about some failure detection schemes that we have. But now we're going to talk about building the repair paths and how they work. Okay? Some observations. There's more redundant data as you have multiple layers of ECMP. So each hop as you're going from a receiver side of the network up to the source, you have more redundant data that's flowing. But what we're noticing is that RPF failures at each level help reduce it. So you have redundant layers. Basically, there's one hop, a second hop, and a third hop. You have the redundant data come to that third hop, and it usually gets dropped because of RPF failures. So the duplicates actually don't go all the way down the tree, and that is really good. If it did, it may be a non-starter solution. Okay. So with non-equal cost paths are used even though longer, they may be less congested where data arrives faster, so more packet loss could occur when there's a local switchover. So that's the key is that if you do switch over, are you receiving packets that you've already forwarded to your receivers? Is there going to be some duplicate data that's being sent? Or if the other side was fast, they're sending new data that you missed on the other path, so would you also miss data? So those are some of the observations. So when we say we can do near zero packet loss, it's a little bit subjective if it's near zero. Okay? So talking about non-equal cost multipath is we made extensions to this proposal to work in ring topologies. A lot of ISP networks have fiber in the ground that are based on ring topologies, and so we want to be able to make it work in that case, because not every node on the ring is equal cost. So what we'll do is we'll distinguish each of the interfaces as ring interfaces. We have two ring interfaces, right? When you're on a ring, at least on one ring, you have two ring interfaces, and then you have these other interfaces that are used as well. And then one of the ring interfaces is the shortest path, or what's traditionally known as the RPF interface, and the other path is called an alternate interface. That alternate interface that we showed in the last example, which you send alternate joins on. Okay? And then you'll accept the join on either interface. That's important. We'll show you in the example next. And that causes forwarding from one ring interface to another ring interface. And when accepting packets on either interface, you forward on the other ring interface. So let's show you an example here. So that we have the source that's directly connected to basically two planes, and we have that ring that's in the center there, and E has a directly connected receiver. Let's start off just focusing on E and see what E does. Well, E's going to want to send a join on behalf of the receiver. You see that the solid blue line is a typical RPF PIM join that propagates upstream towards the source, and that forwarding path is built, and everything is good and happy. This is pretty basic. Now what we want E to do, from its point of view, it has an equal cost path through D as well, right? So just like the last example, it's going to send an alternate join. You see that dotted line there? That's saying it's sending an alternate join because of the MOFR algorithm. D prime receives and says, somebody's just joining me, and he sends a regular join up. I made it a solid arrow line because he doesn't know what the reason of the join is downstream. We made no changes to PIM, the protocol. We made changes to how the implementation sends joins. That's all we did. C prime propagates it up, B prime all the way up to the top, and we have these two paths. So the dotted green line shows you the repair path. It's just like the previous example, E will accept packets, on the RPF interface, but will drop packets there. So that's no different. What we want to focus on is what's going to happen in C and D, right? Because C has the shortest path towards S through B, but it has a longer path through D, going all the way around the ring. So when there's only a receiver at E, any link or node failure on the RPF path is repaired, just like we said. If C has a receiver joined, so out on the left-hand side, if C has a receiver joined, but then B goes down, C's only RPF path then would be through D. So in other words, unicast routing could say, I'm going to switch from B to D, but we don't want to wait for unicast routing to tell us that that's the new path. Okay? So what we want to do is we want E to be able to accept, let's see, did I say that right? So what we want is we want C to be able to send that join, but if it waited, the signaling would happen at failure time, and that takes too long. So what we decide to do is that C will send an alternate join towards D. Now, in the last example, we send alternate joins on an ECMP path. Well, the alternate join you send to D is on a longer path, but it's defined to be a ring interface, so it's okay, it's safe. So what happens is the alternate join gets sent to D. D propagates the alternate join to E. Now notice here, look at D for 1 second. D's RPF interface to the source is the CD link. And C is sending it a join on the RPF interface. Normally that just seems like, why is there a receiver towards my source? Why isn't somebody else upstream worrying about it? But it must accept this join on this RPF interface. And it must propagate it likewise because D is going to receive this join as well on RPF interface. Okay? So D and E only forward to the RPF interface when data is received on the alternate RPF interface. So we're going to see data here come around both directions, right? And when E receives the data packet right here on this ED link, it must forward on the other link. The data packets have to be received in both directions by all routers on the ring, so when there is a failure detected, the data is already arriving at its interface, its other interface. Okay? And so that's how C can get data to its directly connected receiver when, say, the B link fails, the B router fails, or the CB link fails. So that was the last case, showed you that the failure happened on the left-hand side, which was the RPF side. Now we're going to show you that the failure happens on the repair side. Okay? When a failure happens on the repair side, it's also an RPF side from C's point of view, from C prime's point of view. So when C prime has receivers on the alternate path right there, E must forward on the other ring interface as well. So C prime sends alternate joins the same way. This is kind of a mirror image, but just want to make it clear that it doesn't matter if you're on the repair path or the actual path, that you still have to perform the same sort of functions. So if B goes down, what we want to do is we want E to forward packets to D prime because it's receiving packets on its RPF interface. So the basic rule is if you receive a packet on your RPF interface and you know that that's your primary interface, you also send the data on the other ring interface as well as all the other interfaces that lead down to receivers. And when you decided that you have a failure on the RPF path, you accept data on the alternate path, and if the other ring interface is up, you forward there as well as forwarding it down to all the other interfaces where there's receivers. And that's how we solve the problem. So the data is like, it's like FDDI, sorry for the bad comparison, but it's like counter-rotating data that's going around, okay? And you forward it off of the ring only when you know that you're either accepting it on the RPF path or the alternate path. Okay, so an ISP deployment scenario, if you use a cube sort of topology here, you can actually build these diverse paths. And we could see from the cube there that the green path is like a primary path and the red path could be a backup path. And then you have all these pops that are dual located. And what you could do is each side of the cube can be an MOFR ring, just like we described before. And the alternate joins actually bring the data down on each ring. So if you look at the pop 1, you see that black guy right over here is sending a join, and this is his typical RPF join. It's following the shortest path. He'll also send this alternate join over here, and then that will forward along this other path here. All these pop 2 and pop 3 will do the same thing. Okay? So data will be coming down both of those edges as a hot backup. That's the primary data path, and that's the backup data path that would happen to each pop. Okay? Failure detection. This is the secret sauce, I guess, or the hardest part to solve. So if you have direct link failures, they're easily detectable. You lose signal, your local hardware can tell you when you have a link failure. So that's the easiest case to be able to detect a fault. When your neighbor goes down, if you're on a point-to-point link or you're running BFD, you can get that down in tens of milliseconds, right? Usually link failure is a carrier loss, and that's pretty quick too. The hardest part is when something upstream from you, not your link, not your neighbor, but maybe upstream from you has failed. You don't want that failure to have to cause a message to come all the way down to you because it just takes too long, okay? So that's what we're going to focus on the upstream router and link failure times. And of course, you want to use one solution that could detect all cases. So this is what we propose for the failure detection algorithm. We wanted to monitor the data flow on the RPF path. Now, when we say monitor the data flow, all we have to do is count packets, okay? Nothing more than that. We are not asking the hardware to do a lot of new things that it doesn't currently do. So we have these constant bitrate applications that have expected packet arrival time, okay? And you use counters to see if these packets have been received. And how often you pull to look at the counters is your switchover time budget. If you want to be able to switch over in 50 milliseconds, you check the hardware 50 milliseconds at a time. and that would be your polling interval. If the counter doesn't increment within that interval, you know you're not receiving data on that interface. There might be a failure, okay? So if you think you receive no data in that, if the counter doesn't increment in that time frame, then just switch to the alternate interface. If it's a false positive, big deal. You're getting the data down in the alternate path, you can forward it. You will find out some hundreds of milliseconds later if unicast routing said, yeah, you should switch over. Then it wasn't a false positive, it was truth. But if unicast routing doesn't tell you anything and you missed, a packet was dropped upstream or something and you switched erroneously, it doesn't matter, you could keep forwarding data. There's still no packet loss. Life is good. And that's about it. We have original patent, the ECMP example and the failure detection was put in a Cisco patent, and we had the extensions put in another. So this is a IPR disclosure slide. So we have about 10 minutes for questions. Clarence or I could answer any questions. Technical, please.
Any questions for Dino or Clarence?
Eric Coe, Aerospace Corporation. It seemed like you doubled state in the network.
Double stated what?
Double state as far as your receivers and paths that you have to send stuff down within the routers because you have this alternative path that you have to maintain. Is that true or no?
Oh, no, it does not require any extra S, G state. All you have to, it doesn't increase the number of entries that are in your MRIB. Arguably, it could, you need to put a new field in your multicast route to say what is the alternate interface that you're willing to accept on. But it varies on your implementation. You could put it in the RIB and not in the FIB and tell the FIB which single interface is used when the failure happens, because you can normally program your FIB in tens of milliseconds, within 50 milliseconds definitely. Or you can actually tell your hardware to have two interfaces and accept on either one. And when the local failure happens, you could actually, if the local failure happens on the line card, you could actually fix up that entry on the locally. You could distribute it, you could fix it locally, provided that the other alternate interface is on the same line card.
Yeah.
Ann.
Ann Johnson, C-Packet Networks. So right at the beginning, and then just in your response to that last question, you mentioned 50 to 100 milliseconds as being the timing target. But from the analysis that you described, it wasn't obvious that there was actually any timing dependency, given what you're doing in that you're setting up a repair path ahead of any requirement to use that repair path.
True.
So is there any timing dependency at all? For example, if you're trying to do video between here and China, do you actually need to have some link that's within 50 to 100 milliseconds of your last link? Do you have any timing dependency? What happens if your next link is 200 milliseconds away?
Well,
or does it not matter?
Yeah, I mean, very good question. And Clarence and I will both claim that unicast routing and what you have deployed today is sufficient.
Okay. Has any of this actually been tried?
Excuse me?
Is there an implementation? Has any of this been tried?
Yeah, implementations are underway. We don't have anything that's readily testable yet.
So no bits, no.
But you're asking to be a beta site, I guess, right?
Okay.
Thank you. Any other questions?
Okay, thank you very much, Dino and Clarence.